Yeah, hi everybody. This lecture today is on 3D coordinate systems, and we have discussed homogeneous coordinates in the last lecture and how we can represent transformations using homogeneous coordinates. And today we will look into this topic a little bit further and look at how we can concatenate these, and especially what happens if we don't have only moving objects but also moving coordinate systems, and if we describe these coordinates in the local coordinate system instead of the fixed reference system. We will start with group properties of transformations. This is very important to have this in mind when we use all these transformations. You all now have learned in mathematics what a group is. So in our case, we learn that transformations are continuous groups. That means if you concatenate two translations, you get another translation. If you have two motions, one after the other, the concatenated two motions will lead to a combined motion. So this is the group structure. We will just formalize this immediately. And the main thing is that the properties remain after inversion and concatenation. So for instance, motions are length preserving. So if you concatenate motions, we know that the result again will preserve the length of distances between points. The second property is that these are continuous groups. This is very important if we want to do estimation and if we want to describe the uncertainty of these motions and transformations in general, because we can differentiate these transformations with respect to their parameters, and we can apply uncertainty propagation, etc. So let's have a look at it. What is a group? So you know this from mathematics, this is just a repetition. So a group is a set with an operation, here a circle. And in our case, we assume that these elements are transformations, that means matrices, regular matrices, that means square regular matrices. And the operation is the concatenation, in our case, the multiplication of these matrices. So what are the group properties which we use? If you have two elements in a group and you concatenate them, then the concatenated element is in the group. So rotations applied to rotations yield rotations. They are associative. That means you can put the brackets wherever you want. There is a unit element. Of course, in metric algebra, this is the unit matrix. And important is we have for each element an inverse one, which is the reason why we assume that these matrices are regular, that we can use the inverse matrix. We know that matrix multiplication is not commutative. That means we cannot exchange the product of two matrices, because this in general leads to a different result. So we have here non-abelian groups. Abel was a Norwegian mathematician in the 19th century. So we have here non-commutative groups. You already know quite some of these groups. So the general linear group of regular n matrices, also called GL of n is the dimension of these matrices. There you apply the matrix A to some vector and get some other vector. The interpretation of this equation is totally open, because we are just in the mathematical world here. Then we also have a affine general group. This is the AGL of dimension n, and the difference between the linear and the affine group is that you add a vector. That means here in the first case you map a square to a parallelogram with the center being fixed, and here you in addition have a translation vector. That means the parallelogram can be at any place in the plane if we work in 2D. Now, then of course we have the group of orthogonal transformations in 2D that can be interpreted as rotations, including mirroring. That means we have a basic feature. I needed to take a different one than the square because it's too symmetric. So if we rotate it and mirror it, we get a general situation. That means you flip. You may be able to flip some object here, but you only have the rotation around the origin. If you, in addition, exclude the mirroring, you come to the proper rotation matrices, which are called SO2, because S means you have a special orthogonal group, special because the determinant is assumed to be 1. So we only have rotations around the origin. And of course we know the translations and dilations. And now and all these transformations are written in with vectors of, in principle, any dimension. Now we assume that these transformations work on homogeneous coordinates. That means we go one dimension higher, not 2 but 3. And then of course we have motions, which consist of rotations and translations. That means an object is rotated and translated. Or we have the group of similarities, where we in addition have the scaling of the object, as we discussed it, either enlarging or diminishing. Including the case of that there is lambda minus 1. That means mirroring is included in this set, in this group. Now let's have a look at the affine transformations. We just saw that the affine group is the transformation of a vector multiplied with a matrix plus some additional vector. This is in non-homogeneous coordinates. So we have this situation that the square is mapped to a general parallelogram. If we now write this equation in homogeneous coordinates, we have seen last time that this is the product of the homogeneous vector x multiplied with a 3 by 3 matrix leading to a vector x prime, also 3 by 1. And in this case, if we want to represent an affine transformation, we need to have a special structure for this A, namely a 2 by 2 affine matrix, general matrix, regular, and a translation vector. And now you see the difference between using non-homogeneous normal coordinates, as you know it from school, and homogeneous coordinates. The difference is that if we write it in non-homogeneous coordinates, we have here the affine group in terms of mathematics, and here the linear group of transformations. And this is a big advantage because we can use all the properties of linear groups. For instance, the concatenation will use this to advantage. Of course, we have seen that in all cases up to now we had zeros at the beginning of the last row. There are more general transformations, which are perspective transformations in homogeneous coordinates, which map a general square, a square to a general quadrangle. So this quadrangle can be arbitrary, so it could also be flipped. So this is included in this group of perspective transformations. We will not discuss those. They will appear in computer vision or in photogrammetry. Now you see from the discussion that we have a clear transformation hierarchy. So in general, we have here these projective transformations. Then if we have the zeros in the beginning of the lower row, we get the affine transformations. If we assume that the upper 2 by 2 or the upper left matrix is a multiple of a rotation matrix, we have a similarity, which of course has a special case, the dilation, only scaling, or the motion, including rotation and translation. So rotation and translations, of course, are special motions. So keep this in mind if we discuss these different groups, if we apply them. Okay. Now we start a new section which discusses transformations which are passive. That means not the object is moving, but the object is passive, staying at its place, and the coordinates are moving. And the description of these transformations doesn't happen in the original system, or in the world system, or in the global system, how you call it, but in a local coordinate system, a coordinate system which moves with the object during the sequence of transformations. So let's start. We have here the situation that you have an active motion. That means the object is moving from here to here. So you see here the car. Let's say we want to know what this point does. So the point is moving here. The car, we have just a translation. If we have a passive transformation, passive translation, we have that situation. That means the object stays, but the coordinate system is moving from here to here with the same amount as in this case. So in both cases we have a translation, but obviously the coordinates in the first case are increasing and in the second case they are decreasing. That means we have a different situation and we need to distinguish those. Observe that the point here doesn't change its name. So the point x is first described in the first coordinate system with the vector x, and then in the prime system, so to say, x prime, y prime, these are the coordinates of the second coordinate, so we have the coordinates x prime. Here in this case, the point is changing. That means the point changes from x1 to x2 and of course has different coordinates in the fixed coordinate system. So we have to make this explicit when we write down our transformations. Now, to see the relation between the two, I just wrote down this for the translation. So you add the translation vector for an active transformation, or you subtract it for a passive transformation. And this is a general rule that you use the inverse transformation if you apply a passive transformation with the same parameters. So the inversion of IT01 inversion leads to this expression I, doesn't change, and here appears a minus t. So in general, we have the situation that if you transform the point, you move the point from x1 to x2 with a motion matrix depending on parameters p, may include a scale. Then the passive transformation with the same parameters, that means the motion of the coordinate system is described by the inverse matrix with the same parameters. So you see here the x stays the same, so it's the same point which we represent, but we represent in two different coordinate systems which you put at upper left indices. So now that is the first distinction which we need to make, active versus passive transformations. And now we have representations in the original frame, as we discussed up to now, or in the local frame. So if we move with the car and you tell your driver, please go to the right, you don't mean the driver should rotate or rotate the car around the origin, let's say, of your town. But you mean it should rotate around your own position. If you drive with a scooter on a market, then of course you are able to do a rotation on the place. So we have to distinguish these two situations. So let's start with the active translation and rotation. So we first translate by the vector 0, 1, that means upwards. So let's do this. So this is the motion upwards. And the local coordinate system, which we assume to be at the tip of this car, is now at this place. Now, the second motion is a rotation, and we assume that this rotation is described in the original system. So we have to rotate this car around this origin. So let's do this. So the car rotates this way. And we finally arrive at this place with this car coordinate system. And one point of the car, at the beginning being x0, is now at this place. Now, this is not what we would like to describe in practice, so at least if we drive with a scooter, there we would do the following. So the translation, of course, is exactly the same. So we go forward with value 1 and arrive at this place with that local coordinate system, and now we tell our driver to rotate. Let's assume the car can do this around this point locally. So we have this 45-degree rotation to the right as before, and that means we arrive at this situation. So the car is translated and rotated at this point by 45 degrees, and the local coordinate system now is here. So you see this is different. So this is the active motion, concatenation. Now let's assume we want to have a passive translation and then rotation. So the parameters here are the same. 0, 1 and minus 45 degrees. That means a right turn. So the object stays at this place. So the tip of the car is at the origin of our first coordinate system in which we start. So what happens now? We move the coordinate system. So the coordinate system moves from here to here, straight forward in the direction of the viewer in the car, and we have a new coordinate system at this place. So we have the coordinate system x prime and y prime here, and now we rotate the coordinate system by minus 45 degrees, that means to the right, around the origin. Okay, let's do this. So the coordinate system rotates from here to here, and we have the second coordinate system at this place. So we have x double prime here and y double prime here. And the idea is now to describe this point x, which is fixed, which is passive, which is just waiting what happens, in these three coordinate systems, x prime, and x double prime. Now let's assume we describe the motion of this coordinate system in the local system. So we start with the same situation as before. We move the coordinate system straight forward. We arrive at this place. This is exactly the same as we did before. And now we want to we want to rotate it around this new origin. That means in this local coordinate system. We do this and we get this situation. That means we have rotated around this point, and the third coordinate system, x double prime, y double prime, is this one. So again, we see that the coordinates of this point x here are different than the point coordinates x in this coordinate system. So again, we have here two situations, and altogether we have 4 cases. That means we distinguish between active and passive transformations. The object is active or staying. And then we may refer our transformations to the new local coordinate system or to the original. So we have 4 cases, and I wrote down the equations for these transformations. You see here the active and the passive and the original and the local or carried with coordinate system. And we have here the cases A, B, C, D, and you see here the equations are all different. We will go through them now immediately and prove how they can be derived. So you see this is what we knew already. So we first apply the motion 1, and then from left multiplication with motion 2. Here the order is different, is the opposite, and here we use the inverse matrices. So let's start with A, and we see that if you have an active transformation represented all represented in the original system, we have to multiply the matrices, the transformation matrices from the left, M1, M2, etc. if we have more. And if we have the case B, we see that we have an active transformation, but the transformations are described in the local carried with system. So we have now here M1, M2, so the motions are multiplied, the motion matrices are multiplied from the right side. If we go to the Next situation, C, we have a passive transformation. That means the transformation of the coordinate system. We know we need to have the inverses. That means we get a multiplication from the right. And if we have the passive transformation described in the local coordinate system, we have the inverses multiplied from the left. So let's look how these equations can be derived. So the first one is what we already discussed. So we have the first transformation. We apply the motion to our point. The point is moved from 0 to 1. And the second motion transformation transforms it from point 1 to point 2, which is the second motion. So if we combine those, we arrive at this equation. So this is what we know already. Now let's assume we have an active transformation in a local coordinate system, described in a local system. So we again take this example with the translation and rotation. So the first motion is from here to here, upwards by 0, 1. So, but now we would like to describe the rotation around this point. Now, we don't have this. We only have the rotation matrix for rotating around the origin. So, just do the following. We first go back with the inverse motion. Then we are at the origin. Then we know how to rotate around the origin. That means from here to here. That is our second motion. And finally, we take this dark car and move it here to this and apply this first motion, translation, again. So this way we get the transformation from this original situation of the car in the origin with an active transformation, first translation, then rotation, and the rotation is described in the local coordinate system. You could say we could also have done the following: first rotate and then translate, and just do the opposite. Let's see what happens. So the first transformation is that what we already know, from 0 to 1. And the transformation, the second transformation is done in 3 steps. We take first the inverse motion, number 1. Then we apply the second motion, in our case a rotation. And then we move it again forward, in our case a translation. So this is the transformation from x1 to x2 if the motion 2 is described in a local coordinate system. Now, if we then plug in this result from x1, that means m1 multiplied with x0, we get this expression. And now you see, here we have the motion forward, and here the motion backward. Of course, this is the unit matrix, so this cancels out. And what is remaining is that the transformation of our object from 0 to 2 is the multiplication of the first transformation and then right multiplied with the second motion. So this is some trick which we can use. We could also imagine how it happens in 3D, but this is easy to remember. Now let's look at passive transformations. Now what did we learn? We learned that the passive transformations with some parameters are the same as the inverse transformation matrix with the same parameters. So if we have a passive transformation in the original system, we take the case A, which is the active transformation in the original system, that is x prime. And we have to apply the inverse motion, combined motion. What was it? m1 left multiplied with m2. Now we take the inverse, and from the rules of linear algebra we know that this is x double prime. This is so to say the same point described in the second coordinates in the second coordinate system. So x and x here are the same points here described in the original coordinate system, and here after the second motion. So here we have the multiplication of the inverse transformation multiplied, the second multiplied from the right. And finally, we have the passive transformation in a local system. So the active transformation in the local system was multiplication from the right, which was this three-step procedure for the second part. So we have the multiplication of M1 and M2 from the right. We have to use the inverse one because we have a passive transformation. And again, applying the rules from linear algebra, we obtain this expression. That means we have to multiply the inverse transformation matrices, and the second is multiplied from the left. So if you just say, how can I remember? You cannot immediately remember. But the reasoning which I showed you here is something which you can remember. So if you know that the passive and the active are distinguished by the order of the multiplication, and the active and the passive are distinguished by taking the matrix or its inverse, you can derive these equations if you have forgotten them. So here we have all the cases. We have the active and passive and the original and local coordinates in these equations which we just derived. So we have either we work with the original matrices, which we assume these are always active by definition. Colleagues of mine, some take it differently. So it depends on the context. In my lecture, if you define a matrix, it's the motion of some object. So and these matrices can either be multiplied from the left or the right. And the same thing is for the passive transformations, where we have the inverses from the right or the left. So what did we learn up to now? The transformations build a continuous group. The group structure is important that we know that the concatenation of two elements of the same type lead to an element of this type. And the continuity allows us later to do differentiation. And we need to distinguish active and passive transformations and the representation in the original and in the local system. And this refers both to motions, including dilations, or to coordinate transformations. So in both cases we have frames, either for describing some object, the coordinates of that object, or it is attached to our object in order to describe how the rotation or scaling is done. Then we have seen how the concatenation rules look like. Now, we have a problem in notation. So if I write down the inverse, I write down the passive transformation. Remember, this was somewhere here. Here. Here we have the passive transformation with the same parameters. So you take your point with coordinates 1 in system 1, multiply it with the inverse matrix, depending on some parameters, and get the coordinates of the same point in the second motion. Now let's go forward. If I just give you m or m power minus 1, do you know whether m power minus 1 means a passive or an inverse active transformation? This is not shown in the notation. So it's either a passive transformation with the original parameters, or it's the inverse active transformation, which we also might need. So we need to be a little bit more sophisticated in the notation, and I suggest the following. We always work with the coordinates of points, and we assume these are vectors, slanted or upright x, depending on whether we work with the non-homogeneous or the homogeneous coordinates. The name of a point is attached as lower right index. That means we have point x index 1, that means the first point. And the name of the coordinate system is described as an upper left index. That means if you have a world coordinate system, there's an upper left index w, and the transformations use the same indices but they guarantee that we have always a lower and upper index which we could cancel. So let's have a look at what that means. So you have here a coordinate system, say a world coordinate system, with the origin O index W. The system is called S index W, and you have the coordinate axis X upper left W and Y upper left W. Now you have a point here, which is point number 5. So you want to describe this point. The name of the point, or the number of the point, is 5. That means you describe it by this vector having lower right index 5, which is the name of the point, and upper right index W to tell in which coordinate system you actually describe it. You see, this is a convenient notation because it leaves space for a hat if you do estimation, or an underline if you have a stochastical value. So some people write the W on top of it. This is not so comfortable. So this is the description of points. And now we describe an active transformation. So we have here the point xi. It moves in whatever path to point xj, and we want to describe this motion. In the coordinate system xy, we didn't name it. So we have the coordinates of the first point I in that non-named coordinate system, so we don't have some W here or something else. And we want to reach the point X with name J, and we then multiply it with some matrix M, which has indices I and J. So from right to left we see what happens. So first we have I and then we have J. You could also think it's some times, time I and time J. J is larger than I. And the convention is that if you have indices, the transformation matrices have upper or lower indices, and they have to cancel with the indices here. So you have here a lower index and here an upper index. You can cancel it, and you can formally check whether this equation is correct. So there must be a lower index on the right and the left hand side. So if we have the inverse transformation, so let's assume we take this motion from I to J and we want to revert it. That means we want to walk from this point backward to this point. We just need to take the inverse. That means if we take the inverse motion, we can also write this as the motion from J to I. And we know that we just have to invert the matrix. So the matrix M from J to I is the inverse of the matrix from I to J. And you see in both cases we have the upper right index as first index and the lower left index as second index. So now we have a look at passive transformations. So let's assume we have this point xi. This is the point xi, and it is first described in this coordinate system. So this is the coordinate system L. So with coordinate axis xl, yl, origin O index L. And that means this point at the beginning has the coordinates x, right index I, upper left index L. Now we have to multiply it with some matrix with correct indices in order to come to the same point, xi, described in the new system M. So we have a motion of the coordinate system from here to here on whatever path. Here with origin OM, coordinates XM and coordinates YM. And we want to describe this point in this coordinate system. Now what we have to do if we follow our convention, we need to have a matrix with a lower right index L and upper left index M in order to be able to cancel this L here and have the index M, upper index left at this place. So you formally could say we cancel here the indices and we get a lower index right I and an upper index M for the coordinate system. And of course, we have the same situation for the inverse passive transformation. So if we have the transformation from L to M and we want to invert it, that means we want to move the coordinate system from here to here and ask how the coordinates change of this fixed point, passive point. Then we just have to take the inverse. That means we move the coordinate system from M to L, or we use the inverse matrix of Lm, and we get the matrix index M upper left L. So this is a convention which might be useful, and now we need to be able to link motions of the coordinate system and motions of the object. So we know that if we have a passive transformation and an active transformation, they are inverse to each other. So let's assume we have a motion from I to j. That means you have a motion of an object from position I to position j with some parameters. That means this is represented by this matrix. And we want to know the corresponding coordinate system transformation. That means we move the coordinate system, let's say, of a car, and we want to describe something in this new coordinate system. We just have to take the inverse matrix. So generally, we see that if we have a matrix with right index I and upper index j, then if we would exchange I and j, we had to invert. And if we change from active to passive, we have again to invert. That means we have the exchange of the indices and the exchange of upper and lower. So this is, so to say, the matrix of the motion from j to I is the same as the metric coordinate transformation from I to j. So let's make an example. What you see here is an object coordinate system or world coordinate system with origin O and coordinates XO and YO. You have here a car sitting somewhere looking in this direction, and you have here a pole, and you would like to know, if you sit here, in which direction do you see this pole? That's the question. Now, how do we solve this problem? The first is that we have to specify here with certain numbers. So let's assume that the car sits at the coordinate 4, 1, 4 to the right, 1 up, and the pole has coordinates 1, 5. And the question is, in which direction does the car see, the driver sees this pole? Now, the first one is that we have to describe the motion of the car from the origin to its actual pole. So if the car sits at the origin and is moved to this place, we can describe the position and orientation of this car by describing this motion. So we have an active motion from O to C, and this gives us a matrix M from O to C. Now, how do we calculate this matrix? Now we have an active translation by 4, 1. This is this one. So you have here unit matrix and 4, 1. That's the translation. And then we have a rotation by 90 degrees to the left, which is here you have the sign of the rotation angle. That means here this is -1, and here is +1, and etc. And if we know, because we describe this rotation in the local system. So we first move the car here and then rotate it there. That means we describe the rotation in the local coordinate system. We have to multiply this translation matrix with the rotation matrix from the right. So the combined motion from the origin, the car at the origin, to the car at this current position is the product of these two matrices, which is this matrix. You see, here you see the position of the car in the last column, and here you see the direction of the axis, that is 0, 1, that is in this direction, and -1, 0 for the y-axis. So this is the first case. So we now know how to describe where this car sits in this coordinate O. Now go to the next step. Now we want to know what the pole coordinates are in this coordinate system. Now we have a coordinate frame, motion from O to C. This is because the pole doesn't change. It's a passive transformation of the pole coordinates. So what we would like to do is following. We want to take the coordinates of the pole, which are 1, 5, in the original system, and derive the coordinates of the pole in the car coordinate system. What do we need? We need a matrix which does a passive transformation, a coordinate transformation from O to C. Now we don't have this. We have a motion from O to C, but not a coordinate transformation from O to C. But we know now that the coordinate transformation from O to C, the passive transformation, is the inverse of the active transformation. So we just substitute the inverse of the matrix, which we just got in the previous slide, invert it, and multiply it with P. So we take this matrix with 4, 1 at this end and the rotation part, take the inverse and multiply it with the coordinates of the pole, which is 1, 5. The inverse of this matrix is this one, and if you multiply this out, we come to the coordinates 4, 3. So the x-coordinate of this point is 4, and the y-coordinate of this point is 3, which seems to be plausible. And if we now take these coordinates, we get the direction vector. We have to divide by the length. The length is 5, so we get the direction vector 0.6, 0.4, or some approximately 36.9 degrees to the left, because we have the left rotation as default. So this is the solution of this problem. You see how the transformations, the active and passive transformations, are intertwined, and how we have to apply our basic rules, the 4 rules, A, B, C, D, to defining these transformation matrices. So this should be sufficient at the moment. We are now prepared for concatenating any type of motions or coordinate transformations, active or passive, and in 2D. And now we want to go to 3D next time. So we will talk about rotations in 3D and look at rotation matrices, 3 by 3, and Euler angles in order to describe spatial rotations. Thank you very much.